About the Slab waveguide. So as you see in this picture, the Slab waveguide in the Z direction is unconstrained. So it means that waves in the Z direction are propagating wave. So this is the X direction and this is a Y direction. So the Z dependence of a forward traveling wave is the form of e power of minus I beta Z. So the beta is the propagation constant in the Z direction. So the magnitude of the propagation wave number in the core of the waveguide is Kn, which K is the wave number and N is a refractive index. So transverse confinement in the waveguide causes propagating wave mode to have wave vector component in the Z direction. So as you see here in this equation. Effective index. The wave velocity in the Z direction can be considered as an effective index, so which describes the modification of wave velocity by the waveguide. So actually each mode has an effective index that can be defined by beta equal effective index times 2 pi over lambda. So the effective index tells you how tightly the mode is confined to the waveguide core. For instance, for the guided mode, so the effective index is larger than a cloud index and lower than a core index. And for tightly confined to the core, so the effective index is roughly about core index. And for weakly confined to the core, effective index is roughly about clad index. And for the refractive index, or for the effective index is lower than the clad index, so we don't have like guided mode, and all of the modes are unguided or radiative mode. Like this. So this is a simple example that I ran it to the numerical mode, and so in this column you see the effective index. For instance, this is a mode number 1. So for the mode number 1, effective index is 2.445, is around 2.5. So as you see here in this picture, effective index is around 2.5. The refractive index of silica is 3.5 and the refractive index of SiO2 is 1.5. So it means that the light confined through the waveguide. But in this case, we have like in part of the red light, so is on the SiO2 side. For this reason, the refractive index is bigger than the refractive index of clad. So it's around 1.8. But for this one, the effective index is similar to the refractive index of SiO2. So we have a weakly confinement in this mode, and but for this picture, as you see, the effective index is smaller than the refractive index of SiO2, and for this reason, this is unguided. Look at this picture. So we see a different cases for these modes. So another thing that we need to understand in the waveguide mode analysis, so is to understand how we can define a fields. Fields in the waveguide can be classified based on longitudinal field component. For instance, transverse electric and magnetic mode, TEM mode. It means that in the propagation direction, we don't have any component of electric and magnetic field. So, but this is not supported in the dielectric waveguide. So another thing is transverse electric mode or TE mode. So it means that the electric field doesn't have any component in a Z direction. And for transverse magnetic mode, magnetic field doesn't have any Z component. Another one is hybrid mode that exists in non-planar waveguides. So to summarize the wave equations for T and TM modes, we can start with Helmholtz equation. So which del square E plus k square n square equals 0. And after using this assumption, like for T mode, which is easy, equals 0, and using this equation, so we can achieve a wave equation as like this. The second derivative of Ey plus k square n square minus beta square Ey equals 0. So the Ey and Hc both are continuous, and the first derivative of Ey also is constant. So for the Tm mode also Hc equals 0. So we have this equation, the second derivative of Hy plus k square n square minus beta square Hy equals 0, which Hy and Ez are both continuous, and the first derivative of Ey also is constant. But for TE mode, as you see, we have a Ey, and for TM mode we have like Hy. So now we work and we use these equations to continue and solve and find the mode through the waveguides. K is the wave number and refractive index. Beta is propagation constant. For instance, for a specific case, if you look at this reference, principal photonic integrated circuit, so for a specific case, we have Ey, we can find the Ey in three regions. So in the core and in the clad. So imagine that the width of our core is D. I mean, is D, and so in this case, we have a field decay into a cladding mode. We have a decaying mode, like this part, and this part is a decaying mode. But this part, between the waveguide, we have a standing wave solution. And so the other parameter like C, A, B, kappa, all of these parameters can be determined by the wave equation of the Helmholtz equation that you can see. For more detail about this equation, so you can refer to this reference. So now if we plot the electric field distribution, like for instance for 4 different TE modes, we can see here, like this is T0, T1, T2, and T3. So for T0 we have 1 hump, for TE1 we have 2 humps, TE2 3, and TE3 4 humps. So, and also we can see that in the core region, like we have a sinusoidal behavior, and the outside of the core, like we see a decaying behavior. So